All right, so what is asynchronous communication and an example of it in Firebase? So this would be non-blocking communication, right? So this effectively creates a new thread of execution and allows code to run without blocking the rest of the program. Something in that, ballpark. And what's our example of that with Firebase? We've seen our value event listener, which allows us to ask our program to continue to monitor the database at a certain reference for changes and runs independently of the rest of the program so that we can keep using the app but get notified of those changes when they occur and respond to them. Make sense? All right, so that's what asynchronous communication is, and there's tons and tons and tons of examples of asynchronous communication that you deal with on a daily basis. So for instance, on my laptop right now, I have a whole bunch of applications open. I have Slack open, so that guy's running in his own thread in the background, and if a new message comes up, it'll pop up a little notification on here letting me know I have a message. I have my email running, so I might get some emails during class, and so that program is running in the background. It's not blocking me from using Keynote here, using Android Studio. That makes sense? So we have all sorts of examples of asynchronous communication. And from an operating systems perspective, asynchronous communication has allowed us to have multitasking, which is effectively what I just described, right? We have not always had multitasking. In the early days of operating systems, you ran one program at a time. And if you needed to do something else, for instance, if you needed to, if you put things into, actually, we can think about it like in the early days of the iPhone. How many of you had an iPhone like when the iPhone first came out? One of you? Okay. So, when the iPhone first came out, and really for the first several years of the iPhone, if you wanted to listen to music on your iPhone, you couldn't do anything else on your iPhone. You could have one app open. Okay? Because the idea of having more than one application open, even though multitasking was already a very common thing in desktop operating systems, meant that you were using more of your processing power, which meant that you were using more battery. Does that make sense? So then what Apple ended up doing is it said, okay, well, there might be some specific tasks that you might want to do in the background. For example, play music. So rather than having the entire application running in the background, like your music apps like a Pandora or something like that, it could register with the operating system and just play music. Have like a very cut down version of the application running for delivering the music while you were off doing other things. And that's how multitasking ultimately ended up being accomplished on iOS, where Android had multitasking from the get-go. But what did Android suffer from right from the get-go? Horrible battery life. Because its multitasking model was built on top of Linux, which is a great multitasking model as long as your computer is plugged into a wall, not plugged into a tiny battery. So you'd get 15, 20 seconds of battery life on your phone, and you had these special backpacks that people could get that had like the giant laptop batteries in them and stuff like that. And I remember like YouTube videos where people would actually like have a harness for like strapping on like a car battery that would run to like a charger. So you had juice to get you through the day.
Did that actually happen, or is it like?
No, this is real. I mean, these are like early hacks that people have. I mean, you couldn't like go to Best Buy and buy the car battery, phone charger.
I get that. I was just like.
Yeah, no, there were actual people online, who built it as like a proof of concept. Like, look, Our Android lasts all day.
Okay.
As long as you're carrying a, we just took our car battery out of our Suburban, and we're good to go.
That seems very counterproductive.
But funny.
It's got a pretty long battery life.
It jumps.
I mean, that's just as funny as the the old videos where people were like waiting in line for hours and hours and hours for, the ones I remember first were like iPhones, but they've done it with Xbox and stuff where somebody's like waiting in line, they get the thing and they come out right in front of the line and just like spike it on the ground. You've seen these before?
Yeah. Not the spiking on the ground.
Oh yeah, I mean they basically destroy it in front of the line. Like just for the effect. And I think at some point somebody was doing this with Apple Care, because Apple Care will allow, I mean, you get 2 incidents. So they would come outside with this brand new phone that they just waited in line for a day for, spike it on the ground, and walk back in and get a replacement.
It's all about
It's pretty funny. I don't think it was the intent, but it technically worked. Okay, so let's start looking at data structure stuff. All right, so at this point in the class, we've introduced this concept of storing our data from our application in a database, in the cloud, somewhere else, so that we can, when we run our application multiple times, we can bring that data back in, right? So now we have a tool. We have an offset storage location that we can apply to all sorts of different problems. Okay? So we want to identify, so we're going to kind of pause Firebase for a little bit here. We want to identify our current biggest problem with our application. Is this us? This is us. All right, so our current biggest problem deals with this dude right here. So at this point, when we first start our application, before there's anything in the database, or even if there is a few things in the database, we're basically creating this container that can hold, what do I have in there, 1,000? 1,000 patient records. And what do? I fill it up with dummy patients because it has to have patients in there, right? So when I run this guy, big money. So most of my rows, what's the name of this app? Oh, is it still launching?
probably.
Executing tasks, yeah. This is from another class. All right, so when this guy first runs, it's going to show me my couple of things I actually have in the database. Actually, I think I deleted my database, but at this point, it shows me a whole bunch of dummy rows, right? Okay, I have a whole bunch of dummy rows here that are the result of me creating a whole bunch of blank patients, just so I had a array of stuff, right? If I fail to do this, and then I run this again, crashes right off the get-go, because it's trying to grab the patient record from bucket 0, and I have a array capable of holding patient records, but I don't actually have any patient records in there, right? I have a bunch of null values in there. Yet the collection I provided, it has the room for 1,000 things. Now, what I could do is I could create a 0-length array. So if I wanted to, I can come in here to core, and for my patient record array here, I can say that's length 0, effectively wasting my time. Okay. Here's a storage location with no room. It's like you get a car with a glove box that's just painted on, because the handle doesn't actually do anything. There's no room to put anything in here. All right, but you get a functioning application. Okay, and then what you can do is when you add something, you extend your array by 1, update the pointer, add the new thing in there, over and over and over again. Now we get back to that example where arrays are fast, but memory inefficient. Okay, so if we got to put in the notes as just a reminder of that, we're going to say problem with arrays. While they are fast, they are memory inefficient. Remember how arrays work? When we say we need something to hold 1,000 elements, we are effectively saying, I need you to get me 1,000 I need you to get me enough memory to hold 1,000 of whatever my type is right next to each other. What's our word for memory right next to each other? Starts with a C. O. N. Who? What? T. Contiguous. Contiguous memory. Okay, so we need contiguous memory, which is memory next to each other. So we're going to say this is memory inefficient in that we have to go and ask for a big chunk of land, right? If we think about our memory in our computer is kind of like being, a town where we have real estate. We have to go and get a big plot of land to build our big mansion. Right now, we've built a really big mansion and initially have nothing in it. We bought the land, didn't build a thing. And as we build things, we just add little tiny rooms, one at a time. Okay, so you have like enough land to hold a hospital. Yeah, you have like the shed with the lawnmower in it. That's it. That's all you've built on the land. Kind of get where we're going with that? But arrays are fast because they're based on top of contiguous memory. Why does that make them fast?
Reference each other versus based on their place of memory, their memory location, rather than go and look and find it. They already know where it is in memory.
Okay, so given the fact that the memory is right next to each other, if we want to get to bucket 7 of the array, we can calculate the exact place in memory, the exact address where that value lives. So given the base address of an array, that is where the array starts in memory, okay, and this is the value returned by new when creating an array. So when we create an array, it gives us a pointer to the beginning of that array, the base address of that array. And then from there, if I want to get to, for example, bucket 7, so let's say my array is called AR. So AR at bucket 7 is equal to AR plus 7 times type size. So if I had an array of integers, for an example, an integer is 4 bytes, right? 32 bits, 4 bytes. And let's say the base address was 100. This would be 100 plus 7 times 4, which is 28, equals bucket 7 lives at memory address 128. We could just go there. Fast. Okay, so it's fast. But memory inefficient. Make sense? All right. Does that mean arrays are bad? When might we use an array?
We know exactly how many we use.
Yeah. When is an array the right tool for the job? Actually, you're supposed to put the... It always seems weird, right? That you're technically supposed to put the punctuation inside the... It doesn't seem like it should be...
Why is that weird?
I don't know, it just looks weird.
Which we would don't.
Because really, I'm saying the right tool for the job is an idea, and that's where the punctuation would be.
Yeah.
They did that way.
That's grammatically incorrect, I think.
Yeah, that is.
Yeah. Yeah, I think it's supposed to be like this.
Yeah. Just leave it at both. Cover all the bases.
High five.
In our country, it's the other way around. Like whatever you just said, like the punctuation is
So
go
it's not this way?
It's not go in, it's go out.
When in doubt, purposely make it wrong. It's like, well, I'm not sure if it's this one or the other one, so I know it's not this. That's the one you go with. All right, so we'll leave that there. Okay, so when is an array the right tool for the job? When we know exactly how many elements we need to store. We might also say, and maybe put a couple question marks there, when we have plenty of memory to store those things in the event that it is a very large collection. Okay, so, I mean, if you need to store 100 things, you don't need tons and tons and tons of memory for 100 things. But if you're storing a billion things, at that point you might start asking, okay, well, if I need a billion integers, okay, a billion integers, that is, I mean, can I even write a billion? That's 100,000, that's a million, that's 100 million, that's a billion, right? Let's just say yes. We'll multiply that by 4, so that's the number of bytes. So we'll divide that by 1,024, that's the number of kilobytes. Divide that by 1,024, that's the number of megabytes. No, I'm pretty sure this is 100,000, right?
Mm-hmm.
Yep, this is a million. This is 100 million.
10 million.
Oh, 10 million, yeah, so I'm missing a 0, so it's even bigger. Yeah, so we need to divide by another. Okay, so now you need 3.72 gigabytes next to each other in memory. Now things are getting a little more sketch, right?
Mm-hmm.
If you need to store that many integers. So unless you had tons and tons and tons of memory in your machine, or if you had tons of memory in your machine and you needed it to be really fast, you might still go with an array. But this is kind of the thing to consider with very large collections. Kind of make sense? Not a real common thing you're going to have to think about, but if you need to store a bunch of crap, at least ask that question before you consider an array, just because of how it's organized in memory.
And then 10 years from now, 3 gigabytes is nothing, and then it doesn't work.
Well, possibly, yeah. But what may happen is, in that case, you might be storing something or something larger than an int. So even at that point, if you're storing less of them, it might scale up. So we'll always have a problem where something ends up being too big. Just the somethings change. Okay, so here's an interesting question. We have 1,000 patient records in an array. How much memory does that array take up? Okay, now I'm going to trick you. Everybody's prepared?
Okay.
All right. So I'm going to show you our patient record. So here's our patient record. I need to store 1,000 of these in memory right next to each other. How much memory will that array take up? Go ahead.
Just the spot that takes to store the array.
Okay, you've rephrased the question. Not in a great way, but yes, that's what I'm asking. I am asking that. If you're looking for clarification, I am asking how big is the spot that it takes to store the array? That is what I'm asking. How big is the spot it takes to store the array? How big is a patient record?
2 strings.
Now remember, I said I was tricking you.
Include the methods.
Well, no. So this is good. This is where I wanted you to go, by the way. I knew it was going to be a train wreck. Well, we learn more from mistakes than our successes, right? So how big is a patient record, or however I spelled it? If I did, I don't remember if I did two caps, whatever. Okay, so now we're going to go to what you said.
Okay.
How big is a patient record? And we got to store the actual data, right? So we have 2 strings and 2 ints. Well, how big is an int? 4 bytes. This guy's 4 bytes. Well, how big is a string? Strings are objects. So this is actually going to be a pointer, right?
Oh.
Even though we can't access the memory of a string. So the actual size of a patient record will be 4 plus 4 plus size of memory address in that ecosystem. So let's just assume we're dealing with a 32-bit ecosystem right now. If it was 64-bit, we'd have a 64-bit. Actually, let's go with 64-bit since most of our operating systems today are 64. So this is 64 bits, which is how many bytes? Divide by 8, so it's 8 bytes. So this is 8 plus 8, which is 16, plus 4, which is 20, plus 4, which is 24. Okay. So we have 24 bytes. So we have, what do we have? First name, last name, middle initial, age. So we have first name. This is a pointer to a string. So we're going to say that this is 8 bytes, 64 bits. Last name is a pointer to a string. This is 8 bytes, 64 bits. Then we have middle initial. Okay, this is a int, which is 32 bits or 4 bytes. Okay, and then we have a, age, which is also an int. This is 4 bytes, which is 32 bits. So all in all, so this is total of 24 bytes of memory to store a patient record. That make sense? Mm-hmm. So everybody's cool with that? Now, remember, these are pointers to strings, right? So there is a little bit more involved here in terms of actually storing it because those strings have size. So wherever else in memory those strings are, we kind of have to add that to the bulk. But a patient record itself has effectively 2 real values in there, a middle initial and an age, and then it has 2 little pieces of paper. It tells me where I can go and find the first name and the last name. That's what's in a patient record. So that guy weighs 24 bytes. So now we go back to this slide. We have 1,000 patient records in an array. How much memory does that array take up?
24,000 bytes.
You think 24,000 bytes?
Well, that's going off of having the patient record.
So you think 1,000 plus, or 1,000 times 24 bytes? So 24,000 bytes?
Yeah.
Okay. Are you confident?
I'm pretty sure I'm wrong, but that's off of what I know so far.
Oh, so you're not willing to bet your grade on it? Because I told you I was tricking you.
Well, yeah, you told us you were checking us. I feel like that's a pretty good key to say that. No, I don't want to be graded on that, but that's okay.
I mean, you don't have to do any more work the whole semester. It's a free A.
What's the other side of the coin?
Other side of the coin is you don't have to do any more work. It doesn't matter how much work you do the rest of the semester. It's an instant. It's a definite F. I mean, for your own self-satisfaction, you should continue to learn, but you will not pass the class. That's the other other side of the. No matter how you perform.
I'm not taking that one.
This is just a bad bet. What is an array of patient records? Or let's actually go this way. What does an array of patient records contain? Go ahead.
Pointers,
Pointers. Pointers to what?
the patient record
To,
object.
to patient records. Pointers to patient records. In this case, specifically 1,000 patient records, right? How big's a pointer?
8 bytes.
Yeah, we decided for a 64-bit operating system, size of a memory address is 8 bytes, 64 bits. So that means that a pointer to a patient record is 8 bytes, 64 bits. So we have 1,000 of those, right? So 1,000 times 8 is 8,000 bytes. Or roughly 8 kilobytes, a little bit less. 7.8 kilobytes. Big B. See how that works? Now, those 1,000 patient records have weight. And they're strewn all about memory somewhere, wherever the new keyword was ever able to find a little 24-byte pocket for it. Because that's what we needed to store a single patient record. We needed 24 bytes somewhere in memory. But I'm not actually storing the real patient records in my array. I'm storing pointers to where you can find that 24-byte patient record. And then another pointer to where you can find that 24-byte patient record. And even those patient records themselves hold 2 integers and then a pointer to a first name string and a pointer to another first name string that lives somewhere else in memory. That make sense? Mm-hmm. So when we talk about pointers, it doesn't matter if we have a pointer to an int, which you can't do in, you could do it in Java through the integer data type, but if we were dealing with like a language like C and C++ where we have a syntax for dealing with pointers, a pointer to an integer in a 64-bit operating system would be 8 bytes, or the integer itself would only be 4 bytes. Make sense?
Yeah.
Okay, so a pointer actually weighs more than a 32-bit data type like an int. Why does Java make those decisions for us? When we pass an integer to a function, are integers passed by, here, we'll ask this question because this is, notice I'm doing a whole bunch of memory questions right now, right? Because we're about to deal with memory a lot for the rest of this semester. All right. Are integers passed by value or reference? What does it mean for something to be passed by value?
That means it's not a copy.
So usually when you ask a question, you don't get a question back. But you almost never get just a rephrasing of the question like we got from Luke back then. Okay, so you're already above that.
I was trying to answer it, it came out.
What do you mean by a copy?
It's like
Because you're wrong, but you're right.
I'm wrong, but I'm right.
You said it's not a copy, but it actually is a copy.
It's like you can change the value while reference you can. You're just having like a copy. Like either one of them is having that.
Passed by value means we pass a copy of the value. So changes do not
Okay.
have side effect.
I got something wrong with yeah.
Passed by reference means we pass a pointer to the value. So changes do have side effect. We're telling them where they can find the value. Remember the example was, if I give you the address to my house and you go and spray paint my garage, when I get home, I'm going to be in for a surprise. Okay? Or if I gave you my house as a copy and you spray painted that copy, I go home, I'm not going to see any paint on my garage because you had a copy of my house. That makes sense? But copies of houses are heavy. That's why houses are typically not passed by value. We think of a house as an object. That's why they're not passed by value, because to a human being, if you were inviting somebody to your party, you would always give them the address to your house, as opposed to you handing them the house and telling them to open the door at 8. Okay? Now, in languages like C and C++, where we had a direct syntax for working with pointers, as a bad programmer, we could choose to pass the house. We can say, Blaine, party's tonight at 8. Here's the house, open the door then. We could do that in those languages, even though as human beings we would say that never makes sense. So Java, operating off of that idea, wants to make our lives easier, right? C Sharp's the same way. Most of our modern languages are the same way. It says, look, we're not going to make you make that decision, because there's only one right decision. Make sense? The only right decision is, here's the address to the house. So objects are always passed by address. That's where you would go and find it. Okay? Now, I just gave you an example, though. So I'm asking you a question. Are integers in Java passed by value or passed by reference? Okay. They are. So here, I'm gonna do this. I'm gonna say reminder. This is the difference between those guys, right? And then we're gonna say integers are passed by value in Java. So that's what you're saying?
Yeah.
Are you willing to bet your grade on that?
Because I know that string and arrays is passed by reference.
So integers have to be different?
Yeah.
They can't be the same?
Because those two go together, and then the integers and the rest go together. So I know that there's two groups.
So two groups. So you feel confident
Kind of.
that. So you're not betting your grade on this yet?
No.
Okay.
I would rather study.
So integers are passed by value in Java. Really what we can say here is that,
That is right, but
and so here's the support for what you said. And all primitive types are passed by value in Java. Okay? Now, how big is an integer in Java? 32 bits. So size is 4 bytes. Where if we were to pass it by, so we're going to say value size is 4 bytes. Address size would be how big? 8 bytes. If it was a 64-bit version of Java that created a 64-bit memory space. So 64 bits says that's the size of the various data types that the operating system uses. That's probably completely true today. There was a transition period as operating systems sort of were 64-bit. Like you had operating systems that maybe were 64-bit file systems so they could support larger hard drives, but actually were only 32-bit memory managers. How many of you had the Windows Vista, the non-64-bit version of Windows Vista? It actually had a 64-bit hard drive system, so you're going to take really, really, really large hard drives. Actually, I'm sorry. I'm saying the right thing. The non-64-bit version already had a 64-bit file system, so it could give you huge hard drives, right? But the maximum amount of addressable memory was 3.5 gigabytes. So even if you put 16 gigs of RAM in your machine, you would only show 3.5 because there was overhead for the operating system. So it was 4096 megabytes, 4 gigabytes of memory that it would address because it was based on a 32-bit memory manager. Make sense? So interesting things like that, but we're far enough forward now that all the subsystems are likely 64 bits now, but there is room depending on the actual underlying implementation of the operating system you're working with as to whether or not their memory management is 64 bits or, there's probably operating systems for servers and stuff that are running 128-bit memory managers now. And really when we say the size of bits, what we're really saying is how big of a number can I create to address individual buckets? So if I have a 64-bit memory manager, and we think of memory as being just a whole bunch of houses in one big long row, right? So house 0, house 1, house 2, house 3. So we actually only need unsigned numbers, right? So that means I could have 2 to the 64th power unique buckets in memory. That's saying house 0, house 1, house 2, house 3, house whatever that number is.
Hang on, what did you get the 64 from again?
64 bits. So if we're going to represent the number that we can, if we had an 8-bit operating system, so an 8-bit memory manager, that means we can actually only address 256 buckets in memory, 0 to 255. So that means if, let's just say that our average size, let's say our memory bucket size was, we'll just keep it simple. Since it's an 8-bit operating system, we'll just say everything's 8 bits. Okay, so, or 1 byte. So if we have 256 buckets of memory and each one is 1 byte, the maximum amount of RAM you can have in that computer is 256 bytes of RAM. Make sense? Now, you might say, well, let's store a little bit bigger than 1 byte in each of those buckets. That's kind of like if we think about our street here, that each little house is like a little shed. That's the 1 byte size house. Maybe we say, look, instead, we're going to say we can have 256 houses, but each one's a mansion. So now let's say we store 1 megabyte. Now you can have 256 megabytes of memory, total memory, broken up into 1 megabyte chunks. Because you're saying house 0 is a megabyte, can hold up to a megabyte. House 1 can hold up to a megabyte. House 2 can hold up to a megabyte, things like that, right? Now, when you take the operating systems class, you'll learn about kind of the decision-making process. Because one thing we would say is like, well, a megabyte seems way better than a byte. But the reality is operating systems today do not allow you to hold megabytes in a single bucket of memory. It's significantly smaller than that. Okay, it's usually 32 or 64 bits, something like that. So 8 bytes. Well, if we're using our 256-bit operating system for memory management, that means 256 times 8 says we only get 2048 bytes. Divided by 1024, that's 2 kilobytes. Divided by 1024, that's that in megabytes. Divided by 1024, that's that in gigabytes. How many of you think that's the amount of, most of our computers have 8 or 16 gigs of RAM? If we had a 256, or if we had an 8-bit memory manager, and each bucket could hold 64 bits or 8 bytes, that's how much, that's the maximum amount of RAM we could put in our computer. Because that's the number of individual 8-byte buckets we could address with a 8-bit number. So we need bigger numbers. Make sense? So with a 64-bit operating system, 64-bit memory manager, if we stick with that 8-byte, so now we have an 8-byte number, and we have an 8-byte bucket, storage bucket, so each house is 8 bytes big. So now we have 2 to the 64th power. So that's the number of houses, number of buckets of memory we have. Each one of those holds 8 bytes. We'll divide that by 1024, that gets us kilobytes. Divide that by 1024, that gets us megabytes. Divide that by 1024, that gets us gigabytes. So in a 64-bit system, we theoretically could have, what's that number? That's million, that's billion. 137,438,953,472 gigs of RAM. Divided by 1024, or 134 million terabytes. This is theoretical. Make sense? All right, so that's if we had a true 64-bit memory subsystem. Okay, but so we see this as like, oh, well, we don't need that yet. But you saw the 8-bit memory system as, we definitely need better than that. So you see whether, as time goes on, how those decisions have to get made from an operating system perspective. Mm-hmm. How many buckets do we have, and how big is each bucket? Because the idea is you don't want to make the buckets too big, because then you might have wasted space. How many, so let's use that example from a few minutes ago where I said 1 megabyte buckets. How many files on your computer, just out of the blue, make a guess. What percentages of the files on your computer are 1 megabyte in size? Small percentage?
Yeah.
You know, most of our files are fairly tiny files. 1K, maybe even less than a K, something like that. So if you stored a 1K file inside of a 1 megabyte bucket, what do you have? 1,023K of wasted space. Which means you're not taking full advantage of your RAM. Because you can only store one thing in that position. So now you throw that 1K file into your 1 megabyte bucket. And that bucket's almost completely empty, but it's currently occupied by that file. So you want to find the sweet spot. What's your average file size? Or what's the chunk you can divide your files into? Because that's usually, our current memory managers use something called paging. So that when we do store the stuff in memory, we have the least amount of wasted space. Now, the perfect amount of never wasting space is to have 1-bit buckets of memory. That's a lot of, so if we use the 1-bit as an example here, let's go back here. So now we're not storing 8 bytes. We're storing not even 1 byte. We're storing 1/8 of a byte. That's a bit, right? So this is 1/8. So that gets us the total number of, so we have this many numbers times this many bucket size. So that's our total number of bits of storage. So we'll divide that by 8. That gets us bytes divided by 1,024. That gets us megabytes divided by 1,024. That gets us, let's see, hold on. That's the number of bits. That's bits, so we do divide that by 8. That gets us bytes. Then we divide by 1,024. It gets us kilobytes, megabytes, gigabytes. So in that same system, we could have 268 million gigabytes of RAM, which is actually still pretty good for 64 bits. Then you'd have no wasted storage, but addressing would now be will be slow, because now you have to get to house number 2 to the 63rd power all the way down the street down there, which is like basically a road trip to the other side of the country or something like that. Go ahead.
Would it be, if I can just hypothetical situation, would it be efficient to have like 2 separate RAM cards that are running different sizes, or like 2?
I mean, potentially you can test all those different things. Those are more operating systems concepts, but the answer is probably not. Otherwise, we would see computers like that. Yeah. So there's a trade-off between wasted space and memory access speed. These are all operating systems concepts. But punchline is we've kind of reminded ourselves how memory works, okay, for us in here. So now what we want to do is we want to look at something called a linked list. Okay, and actually before I say linked list here, I'm gonna make a slide that's called linear linked data structures. And we're going to look at 3 different linear linked data structures. We're going to look at linked lists. We're going to look at stacks. We're going to look at queues. All right. Then we're going to end up looking at nonlinear linked data structures. And these are going to be our trees, binary trees, AVL trees. Then we'll look at also graphs. Okay. But we're going to start off with linked lists. Now, first of all, as always, you can't use the built-in linked list class or any variation of it for your homework assignments. What does that mean? You have to write your own. Okay? Make sense? So when you Google stuff and you see them implementing doing something with linked lists using the built-in linked list type, that's great. When you're doing this professionally, you will certainly want to use the built-in linked list type. But for right now, we're learning about making linked lists and how they work. So you'll be writing your own linked list. Make sense? So if you turn something in that uses Java's built-in linked list thing, it's just a 0. I'm not going to waste my time. It's probably the rest of that's Googled too. Make sense? I want you to understand the stuff. Okay. Linked lists. We're going to call these guys an alternative to arrays. These are not necessarily better or worse. We want to think about what's the right tool for the job. So a linked list is an alternative to an array. It is relatively slow. It is very memory efficient. Whereas arrays were relatively fast and not memory efficient. The alternative, the antithesis. Does that make sense? Now, I specifically write relatively slow here because we're still dealing with computers. So when you think about possibly using a linked list for something, I don't want you to go through this thought process of, well, do I really want this my program to drag along and be like noticeably sluggish? That's very, very, very likely not going to happen unless you're storing some really strange things. Okay? Or you're dealing with a really, 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 really old computer. And even then, you probably wouldn't notice. Okay? So they're not slow, because our computers are fast. Right? But technically, if we were dealing with a foot race, it's probably Usain Bolt versus me, but worse. We all know who Usain Bolt is, the really fast guy. And none of you have seen me run, but you can probably assume I'm slower. Probably a lot slower, right? Yeah, just don't. But you don't think a lot is even enough?
I'm just watching you on the Olympic track right now. Picturing you with the golf cart.
I saw recently. I think he'd still beat me.
Oh no, I'm sure he would. But
Yeah, I think I would. I think you have to be on horseback to beat him. Yeah, that's actually an interesting question. It's possible he couldn't beat a golf cart. I don't know.
I think he has a golf cart, right?
Depends if you got the governor on or off.
That's true.
You probably could soup up a golf cart to beat Usain Bolt. That's a YouTube video.
Oh, yeah. Wish I had a go-kart, one of those.
There was some show I saw a couple of years ago or something that was like Man versus Beast, where they had it was actually many years ago, where they had human beings, like professional athletes, competing against animals and different things. Like they had some runner guy race a zebra, and just a straight foot race. And then they had, but sometimes it's difficult to get the animals to cooperate, right? And they had some NFL guy go against I think it was a cheetah in like some sort of agility track thing, going back and forth. Yeah. It might have been a jaguar. Some animals known to be very agile. I think it was a cheetah. I think it was a cheetah. But then they also had the hot dog eating guy Kobayashi going up against like a grizzly bear. That's the best one. Because this guy, you kept winning the hot dog contest, eating like 75 hot dogs, in 12 minutes or something. But they had no buns for this because I guess the bear won't eat bread. So it's strictly low carb. So you have Kobayashi, standing there. They had him in a cage next to the bear for protection, right? They covered him in coconut oil, threw him in the same cage. No, so he's there like ready to start eating the hot dogs. There's just this pile of hot dogs in front of him. It was like 200 hot dogs or something. And then they just released the bear into the room, and the rule was that the competition starts when the bear begins eating. Okay, so who do you think won?
Bear.
This was a giant bear, first of all. And you're like, is the bear going to actually eat the hot dogs? He mowed through 200 hot dogs in like no time. I mean, he was like, he was licking them into his mouth, right? Taking 5-6 hot dogs in a clip. I mean, it wasn't even close. You should YouTube that sometime. Just do Kobayashi versus a bear. Don't do it right now. Put it in your notes to check it out later. But it was,
Spell his name.
I don't know. It's Kobeyashi. Kobayashi.
Okay.
Kobayashi versus bear hot dogs. Something like that. It's pretty funny. But the bear just owns him. You're just not sure the animal's going to cooperate, but apparently bears like to eat, and he liked hot dogs. Yeah, because then he started like trying to go at the cage to get to the other hot dogs. That Kobayashi, he wanted more hot dogs. This guy wasn't done.
Is that like something they made up, or is it like real life story?
Well, no, I mean, this is not a cartoon. This is a real human being with a real bear in a cage next to him eating hot dogs. Yeah, they had to stretch to see if bears would eat hot dogs, but the short answer is yes. They will eat hot dogs. But they're strictly low carb. That would have been really funny to see how the bear would have handled it if there was hot dogs in the buns.
Mm-hmm.
Like, would he have like picked them apart, or would he have just eaten?
Probably just eaten still.
Yeah.
Probably just didn't take a little bit longer. But like for
A little bit longer would not have made a difference.
Yeah, no.
I mean, he was moving the table the hot dogs were in with each bite. I mean, he was eating aggressively. All right, so let's think about linked lists. How did we even get onto that? Oh, the relatively slow thing. Computers are really fast, and what if you had an eating contest versus a bear? Oh, that's great. Okay. So here's an example of a linked list. All right, so I'm going to... It's not clicking. There we go. This is going to be my value. Oh, what happened? Oh, I'm in a different class now. There we go. All right. So we're going to have, I'm just going to fake a variable here. So I'm going to have a linked list LL is equal to a new linked list. We're going to build this guy. All right. We haven't built it yet, but we will have an object called linked list. All right, so we're going to have a variable here named LL. All right, this guy's going to have some memory address. I'm going to actually make it up, ABF. The ABF memory address, hexadecimal, let's say. Okay, so that's that memory address. Now, a linked list is going to keep control of one variable, a variable called head. Right now, that guy's going to be equal to null. So we're going to start writing some of this stuff down. We're going to say a linked list has a node called head. This guy points to the first element in the list, or null if the list is empty. Okay? What's a node? A node has two parameters. Has a payload. This is the value the node holds at this bucket. So that's where I'm connecting it to arrays. So bucket 0 might hold a 7, bucket 1 might hold a 13, for instance, if we're holding integers. Okay? So the payload is going to be some type, and this is the type value the node holds at this bucket. And then it also has a node called next node. This guy points to the next node in the linked list, or null if this is the last node in the list. That make sense? All right, so we have a linked list is a collection of nodes where head points to the first node, that node will point to the second node, that node will point to the second node, or to the next node, so on and so forth. Those nodes are spread out all over memory. They are not contiguous.
Okay.
Every single time you add a value to your linked list, a brand new node is created with the new keyword, with its value being set to payload. So that guy's going to live somewhere in memory, and the previous node will point to wherever this guy is in memory. I'm going to draw a picture of this. All right, so linked list has a head. Now, we might keep track of a couple of other things in linked list. We might keep track of a count, so the number of elements currently in the list. And then there's some known helpful functions for generic linked lists. So we have add front, add end, remove front, remove end, add at index, remove at index, and then maybe like display. So this will show a textual representation of the list for testing, something like that. So that we can check to see if we just called add front, that our list now has that new value added to the front of it. Or if we say add end, we can display it and see that the new guy shows it at the end. Make sense? Okay, so these are the common things that a linked list might provide. Now, realistically, if we were just trying to build a linked list for our patient records in our example here, we actually only need to be able to add to the end. We start off with an empty list, and then just as new patient records come in, we just add. So it's a very simplified version of a linked list. It still has a head. It still has a count. We just only actually have to implement one of these functions. Okay? But for the next couple of classes, we're going to be working with linked lists in general format, not necessarily applying them to our patient records yet. Make sense? So that means we're going to write all of these. And that means you're going to write some of these. And they're a lot of fun. Okay. So a linked list will look something like this. I'm going to create a simple linked list example here. So let's say we have a 7 is my payload. And then this guy also has a, just put next there, and we'll make that guy green. Oh, I meant it to be red. I just said green. All right, so now go ahead. I'm going to take this away just so the head has a value. The value will be the address where this node lives. But I'm going to take it away just so the picture looks correct. So initially, when we create a blank linked list, that brings our linked list into existence. This is the memory address of that guy. I just made one up. Okay? So now you have a head variable that points nowhere. This is an empty list. Now, if I were to say ll.add end, for instance, 7. So I want to add a 7 to the end of my list. Actually, I'm going to add it to the front of the list. I'll have you write add end for your homework because it's a lot harder. All right, so we're going to add front. So the first thing we ask is head pointing to null. It is. So I could just go ahead, I create my new node here, and I can just make head point to that guy. Super easy. And this new node, his next node, currently points nowhere. Now, what if I then say, I want to say ll.addFront2. I'm going to bring a brand new node into existence. Here's my 2. Then I'm going to say, okay, is head equal to null? It's not. So what I actually need to happen here is I need, now if I immediately do this, if I say head points to this guy, what have I just done? I've abandoned this node. He's going to get automatic garbage collected. Nothing points to him now. So I've lost the old front of my list. So what I need to do in order for this to work is I'll build my node. I'll make this guy point to the same place that head points to. I'll scooch this guy over just a hair. Okay, I'll make this guy point to the same place that head points to. So now you have 2 pointers that point to the same node. Then you can update head to point to the new front. If I say add front 5, I ask the question, is head null? Nope, head points to a real place. So what am I going to do? I'm going to make my brand new node point to the same place head points to, and then I'm going to make head point to this guy. I'm adding it to the front of my list. See how that's working? Okay. So I need to turbo this for a second. So I'm going to say new Java class. I'm going to create a linked list class. I'm going to say new Java class. I'm going to create a node. And for our example right now, we're going to hold integers. So I'll say private int payload. And then I'll say private node next node. When I build nodes, they take the payload as a parameter. And they initially have the next node pointing nowhere. Now I need to be able to get, so I'm going to generate my getters and setters here. I need to be able to get my payload and my next node. And then I also need to be able to set my next node. I don't get to set my payload, because my payload's set only when I first get created. So that's what a node looks like. a linked list. We'll have a private node head. Public linked list takes no parameters. We say this dot head is equal to null initially. We say, I'll go ahead and give it a count. Private int count. This dot count is equal to 0. Then we'll say public void add front int value. We'll say node n is equal to new node, passing it value. So I'll create my empty node. We'll ask the question if this dot head is equal to null. That means I have the empty list, so I'll say this dot head is equal to n. Else, I'll say n dot set next node to the same thing head points to, and then I'll say head is equal to n. Either way, I increment count. I'll write a quick little display method here. You're going to have to go through this by hand to understand your homework. This dot count, I++, and I will say, let's just build up our answer here. So we'll say answer is equal to cur_node.getPayload. We're going to say answer is equal to answer concatenated with cur_node.getPayload, and I'll add a little arrow after that guy to make it look all linked listy. And then cur_node is equal to cur_node.getNextNode. So that's how display works. I'll go into my main activity. I'll test this real quick. I'll create a linked list called LL is equal to a new linked list. I'll say LL.add front 7, LL.add front 2, LL.display. And just for the sake of being able to easily find it, I'll put some asterisks there at the beginning of our answer. I'll go ahead and run this guy. I'll look at logcat here. This is where's my output? Well, it's in there somewhere, but this is showing a different database. That's my patient record. And this guy is, well, I'll look at it real quick just to get it set right before I push it. But this is going to show me, because it's actually it's showing me the output from my 518 app. The code currently works. So this should show me an output that looks like this. 2 followed by a 7 followed by an arrow, and actually right now it'll have some asterisks in front of it, so it'll look like that. Okay? So I'll make sure I get it running off the right thing before I push it. But your assignment for Thursday is to write add end. So we've written add front to add things to the front of that list. So go through and understand how this guy works. It's not very hard, just draw pictures. And then you're going to have to write add end, which will require you to walk to the end of the linked list. That is, get to the node whose next node points to null. Okay? The end of the list is the last node in the list where you have a node whose next node is nothing. All right. Remember, today, student, faculty, staff, Bible study, God, and grub. Go to the cafeteria, sign in, get your free lunch. Take it down to the terrace room. It's from noon until 1.
Excellent, man. Do you have time tomorrow?
They have time tomorrow?